Green flow. Hello and welcome back to Calculus 3. This is section 13.7 on change of variables. Last class we looked at the transformations. Something similar was done in Calculus 1. It was called U substitution, section 5.5 in your Calculus 1. But now we have double, triple integrals. So we have multiple variables, x, y, z, and we would like to transform those on the into a different plane. So let's say you have x and a y. X and a y would change into, let's say, uv. And then we can have x, y, z transform into uvw and so on. Now, earlier, you only had to worry about transforming function because your input, the domain, was a simple number line, which technically stays unchanged, whether it's input x from negative infinity to positive infinity, and then u from negative infinity to positive infinity. Well, you had limits, you had to transform that. But now the trick is that it's not just we are transforming functions, we are also transforming regions. And what might be, I don't know, a rectangle, when you transform it, might be a semicircle or something like that. So transformations now get to be much trickier. So we first look at the transformation of region, which I did the last time. We have these transformations that I already completed. That will be posted in notes. One of these is done in the textbook already. And let's go with the now next building block. So after we transform the region, we're also going to need something that is called Jacobian Matrix. So the determinant of Jacobian Matrix will be the equivalent part of that transformation of dx into du. So we are talking about Jacobian Matrix, the determinant of so in two variables, Jacobian matrix will be given as the determinant of partial x, partial u. Now these are all functions. Partial x, partial v, partial y, partial u, partial y, partial v. And you know how determinants are computed. I'm going to erase this. You do this. So you have dx, du, dy, dv minus du, dx, dv. So this is the matrix for 2, and then we also have the one for 3, right? If you have UVW. So I'm going to actually, you know what, I should define that one right away so we don't have the issue. Without going crazy with all of the intermediate steps, let's just write what is necessary. Okay, so partial x, partial u, partial x, partial v, partial x, partial w, partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, partial z, partial w. So that's for 3. I don't like this box. No coffee. So we have a 2D and a 3D ones. And now the transformation itself. So change of variables. If you have the double integral over region R of the function x, y, dA, you look at a thing and you can't integrate because whatever, you're supposed to change variables and then you should be able to integrate. So what you do is it will be now the new region S, which is your transformation. You will have f of g of uv and age of uv. So those are the two transformations times the Jacobian of uv dA again. Now this will be obviously in terms of u and v. So this is change of variables. And now obviously if you put the 3 x, y, z, right, you will just have one more of these functions. Jacobian will be also in terms of 3. All of the dAs will be dv's. So it turns out to be the same thing. Want to see. Okay, so let's start. Each one of these examples takes about 3 years to do. so let's start. Integrate square root of 2x y minus 2x dA over the region R, where region R is given as all the points x, y, so that you have a parallelogram with vertices 0, 0, 0, 1, 2, 4, and 2, 5. Use transformation. Now, the transformation is given. Usually you have to figure that on your own. X equals, so use transformation t, x equals 2u, and y equals 4u plus v. Great. So this is example. So let's see how this works. You start from, got the parenthesis here. So you start from transforming the region. That's always the first case, because once you write your new double integral, it has to be integrated over region S. That's a new region. What's given there is region R, the original region. So I'm going to draw region R first. I have 0, 0, 0, 1, 2, 4, and 2, 5. So this is region R. in xy. And we need to transform this region. So let's take a look at these vertices. Point 0, 0, which is x and y. We need to transform that into uv. So if you take a look, it's going to be a little bit tough to do it this way. So let's first transform, flip this around. U is equal to x over 2, right? And the v is equal to y minus 4u, but then v is equal to y minus u is x over 2, so 2x, right? You put u to be x over 2, that cancels, yep, so 2x. So these two are going to transform all of the points. So if I have a 0, 0 as the input, as x and y, then what is my output as uv? Well, stick 0 here, you get 0, and stick 0 here, you get 0. So 0, 0 goes into 0, 0. Awesome. What happened? You should check that out. Then you have 0, 1. We plug in 0 for x, we get 0 here. And then when you plug 1 here, you get 1. Right? Because x is 0, so 1 minus 0 is 1. Good. The next point is 2, 4. So plug in 2 for x, we get 1. And plug in 4 for y, we get 0. Okay. And then 2, 5. 2, 5. I get 1 and 1. Now look what you get in your UV realm. 0, 0, 0, 1, 0, 1, 1, 0, and 1, 1. Hey, look at that. This is region S. Perfect. Yes.
So did we change the region just because it was easier, or because we couldn't do it that way?
You had to change it because you have to change dx into dv. You have to change the, sorry, that was the wrong analogy. You have to change the limits of integration. If you are, I'm going to erase all of this. If you have the integral of square root of x minus 1 dx that goes from 2 to 5, you cannot integrate this way. You have to use u sub, right? So you will say u equals x minus 1, and then du equals dx. So these are your, so this over here is equivalent to this, okay? And this one is the Jacobian, okay? Now, what is the region? The transformation of region is that now when you do the integral and you write root u du, you have to change these guys. Changing these guys by saying that u is equal to 2 minus 1, which is 1, and u equals to 5 minus 1, which is 4, write these 1 to 4. So you know that when you have a double integral over the region, you look at the region and you put the limits on the integral, right? Yeah. So that's why you have to transform region. So transforming the region is actually fixing the limits. Then, I haven't done it yet, transforming the actual function to get this part, and then doing the Jacobian to get this, which is the reason why these problems take so long to solve, because you have all of these things. And technically, this is like the ultimate thing to practice for your exam, because this contains everything. Depending on what kind of region you get, you either get rectangular or a general region, so you know how to set up the integral looking at the region, plus everything else, right? So now, the next step, so we have the yes? Well, how did I get integral square root of x minus 1 dx, and why did I say x minus 1? Right? It's called the experience. It's called, right? So the reason why it's, figuring something like this out is actually a lot of trial and error and figuring out different things. You might be transforming the region so that you have the easy region, or you might be transforming something that will fix the function inside that it's easier to. So it depends on the problem. So you should all be happy when this is given to you, because you don't have to look for it, right? Because this is already enough of torture, right, in order to transform it. Anyway. Yes. Well, you will probably have a part of this for the test, because these problems really take like 40 minutes to do, as you can see. We are currently working on probably the easiest example that it's out there, right? So, all right, so now what do I need to transform? The next part, what was that? It was square root of 2x y minus 2x. So I need to change this now into something that it's uv. So what do I have for this? I have that x is equal to something and y is equal to something. X is 2u, and v is y minus 2x. No, I need y equals what? 4u plus v, thank you. So you plug these in, and you grind the algebra. So we have a square root of 2 times x is 2u, in parentheses y is 4u plus v minus, and then 2x is going to be 4u. It becomes 4u, and in parentheses, what do I get? These guys die, I just have v, right? Well, that worked out nice. So this is technically 2 square root of uv. Whew, nice. Yes, right? Awesome. So that is the transformation of the function. So that was equivalent, if we are still looking back into our integral x minus 1 dx, that was the part where you write square root of u, right? When you transform this piece to get that piece. So that was it. And now the last part is for us to get the Jacobian matrix, which is that dA part at the end. So working on a du portion of it. So Jacobian matrix of uv. So that will be determinant. And now we have partial x, partial u. So we are looking at, I'm going to write it partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So just plug everything in. Partial x, partial u is 2. Partial x, partial v is 0. Partial y, partial u is 4. And 1. So it's 2 minus 0, 2. Sweet. Are you going to end up with a function in terms of uv sometimes? Hell yes, right? Remember, this is the easiest example. So we got 2. And now I have double integral over region S of 2 square root of uv, times 2 and then dA. The region S is 0, 1, 1, 1, and 1 square, which means that we can set it up any way we want. 0, 1, 0, 1, 0, 1 of 4 root uv du dv, or dv du, doesn't matter because it's a square. And we transform that really bad integral into something that is easy to calculate. So if you get 6 on this one, that's the actual answer. There are no transformations back or anything like this because we actually have the limits and we are getting a value at the end, right? So that's it, we're done. So all you need to do now is to integrate. So if you're integrating in terms of u, v is a constant. So you just compute. So this now turned into a 13.1, right? Rectangular region basic integral. For 0 to 1, the integral in respect to v stays. The integral of root u is u to the 3 halves divided by 3 halves from 0 to 1, and we still have dv to deal with, which is equal to 8/3 integral 0 to 1 root v dv, which is 8/3 v to the 3 halves and then 3 halves from 0 to 1, which is 16/9. And that should be the answer. So number 1, transform the region. Number 2, transform the integrand. Number 3, do the Jacobian. Then plug them all back. Then look at the region, write the limits, and then finally do the integral. Now you do all of these things and you end up with something that you still need to transform into cylindrical or spherical or polar, right? After that, these problems can't just go on and on. It's time to integrate. Hey, it's a trig sub, right? I know. I can make your wish come true. Okay, integral over r. Look at this beauty. Morning. Take a cookie. So this is our next square root, right, that we want to integrate, and the region is given as this 45-degree rotated square. With points 1, 1, 2, 0, 1, -1, and clearly 0, 0. So this is region R on X. Can we transform this? Now, Joe, you asked, how do I figure out what can I do? see, over here I see these groups, right? Like these two groups. So why don't we try and have u equals x minus y and v equal x plus y, and see if we can get anything from there. Because any time when you're doing this substitution, if you can make one variable to be the numerator and one variable to be the denominator, you're immediately bypassing a lot of stuff. You don't want to have the same variable u and v in denominator and numerator, because then you have to do further substitutions and further stuff. But if they are completely separated from each other, then the top one is just square root when you integrate u out, or v, and the bottom will just be 1 over that, 1 over v, which would be ln, right? So they're both easy to integrate when they're separate. If I come up with some kind of substitution that would have u on top and u on the bottom, then it's further substitutions and further partial fraction decomposition or trig sub or something like that, right? So what I'm doing here is I said, all right, so if I make this u and make this v, then I have two completely separated integrals to, right? I'm detaching numerator and denominator. So when I integrate in terms of, but then is it guaranteed it's going to work? Hell no, because Jacobian can mess it up, right? So but we see that Jacobian will not mess it up, because all partial derivatives over here are either ones or zeros, right? And if we have that, that's going to be a number. It's not going to be a function. So it can't mess it up. Who put this desk over here? All right. So the question now is, now this is a difficult part. To go to region S, I have to figure out this in terms of x and the y. But I have x and y in both equations, right? So now, to get x equals blah, blah, blah in terms of u and v, and y equals in terms of u and v, I actually have to solve the system. Great. Let's do that now.
So you could like come up with a transformation and just you could work out, well, probably be wrong when you get to the
it would not be wrong, it would be just not the right one. How would I say? Yeah, still wrong. Yes. But the trick is that when you don't have squares in here, right? You don't have squares, you don't have sines and cosines and e's, then Jacobian can never mess it up, because all of these partial derivatives, they're going to work as constants. And if you have them as constants, it's just going to be like in the previous example, times 2 or times 5 or divided by 2. So that they're not going to be an issue. All right, so now what I'm going to do, I have to solve the system x minus y equals u and x plus y equals v. I'll add the equations and get 2x equals to u plus v. Great, so x is actually 1/2 u plus v. And if I subtract equations, I will get, so I subtract equations, let's go bottom minus the top, or top minus bottom. So if I subtract equations, yeah, bottom minus the top is better. I get 2y is equal to v minus u, so y is 1/2 v minus u. So there they are. These are the ones that we have to use to transform our region S. So now transformation. What do we have? We have a point 1, 1, which is x and a y. We'll go into a point, plug 1, 1 into, what do I have here? Plug in 1, 1, x and a y, you get 0. And plug in for v, right, because we're getting uv now, you get 0. So 1, 1, no, you get 2. So 0, 2. The next point we can convert to 0, 0. So convert 0, 0, it stays 0, 0. Convert 2, 0. Convert 2, 0. So that's going to be 2, 2. And convert 1 and negative 1. So x is 1. It's going to be 2. And 0, right? Nice, it's a square. You have 0, 0. Here's your 2, 0, 2, 0. Here is your 2, 2. There you go. Zero, 2, and 0, 0. So this is your region S. On my home planet, this means hope. No, I'm serious. I hope this problem is going to work out. So now, this is easy transformation because we already talked about it. We set it up. So this is u over v plus 1. Right? So that's easy part. And now the final part is, you probably go, so why did you do this? We never used it. Jacobian, right? Because Jacobian is partial x, partial and partial and partial, right? So now we use that. So Jacobian of uv, I keep writing this so you memorize it. Partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Now they're all 1/2, and then so partial x, partial u, and partial x, partial v are both 1/2 each. And partial y, partial u is negative 1/2, and this is a positive 1/2. Great. So that's a quarter plus 1/4 is equal to 1/2. Remember that the equation is go this way and then subtract. So that's minus and minus together will give you a plus there. So Jacobian is 1/2. Great. I have double integral over region S. I am integrating this guy times 1/2 as a Jacobian dA, which works integral 0, 0, 2, 2. And then I'm going to separate this as a square root of u as a square root of v plus 1 because I can. I'm going to kick 1/2 outside because no one cares about it, and then put du, and then do dv because dv is going to give us ln, so I want to do that at the end. All right, so 0 to 2, there's a 1/2 in front. 1 over square root of v plus 1 is a constant because I'm integrating in terms of u first. The integrating square root of u is u to the 3/2 divided by 3/2. Computed from 0 to 2, and I still have dv to deal with. The 1/2 and a 2 will drop, so now you have 1/3 in front. Integral 0 to 2, and we still have 1 over square root of v plus 1, and when I plug in 2, I get 2 root 2, right? Because it's a square root of 8. So 2 root 2 and dv. So 2 root 2 is a constant that goes out. So 2 root 2 divided by 3, integral of 1 over, let's put v plus 1 to the negative 1/2 dv from 0 to 2. 2 square root of 2 over 3. So now this is plus 1/2, so it becomes v plus 1. Oh, did I say earlier was ln? I lied. I clearly lied. Computed from 0 to 2, which is further equal to, plug 2 in, so I get 2 root 2 over 3 times square root of 2, so another 2 root 2. 0 will make it a 1, so I have minus 2. And when I distribute through, I get 4 times 2 is 8/3 minus 4 root 2 over 3. So I believe this would be the answer. Hopefully. Yep. Got it. Good enough, huh?
Yeah, I don't know.
I don't blame you. System of equations. So the question is, how do we go from substitution, which is u equals the mass into x and y equals, because you must have this in order to do the Jacobian. Well, you solve the system. You see the system x minus y is u. So think of it as in algebra x minus y equals to 5 and x plus y equals to 3. And then as you change them, they will be like you add them and it's 5 plus 3 is 8. Well, now you don't have 8, now you have u plus v. So when I add equations, I get 2x. These guys cancel, u plus v. And in order to get x alone, I move a half to the other side. So now x equals everything else in terms of u and v. The previous example, I didn't have to do the system because we had that, I believe, u was equal to 2x. So x was u over 2, like this, right? So no need for a system. The next example is far worse because now we're going to have nonlinear cases here. And the nonlinear substitutions lead to Jacobian being non-constant. Jacobian will be in terms of u and v, which angers the situation further. And then as soon as you think that everything was finally settled, then it's time for 3 variables, which makes even more fun. Ah, there we go. Z crash. So say that we are integrating just y squared dA. And you say, why in the earth would you transform this, right? It's easy, y squared, just integrate. Well, the problem is that the functions that the region R, right? So region R gets to be this nasty region. It's in between x equals y squared, x equals y squared minus 4, x equals 9 minus y squared, and x equals 16 minus y squared. So now that is the series of these parabolas that go like this, and your region R is here. And it's absolutely crazy. So, as you know, the integral looks easy to integrate, but the region is insane. So you will have to probably break this over 3 or 4 integrals, and then, you know, good luck with that. So what can we do instead? Let's see. U equals x minus y squared, and v equals x plus y squared. So I'm going to immediately transform this because I have a system. If I add equations, right? So if I add equations, I will have 2x, y's are dead, so 2x is equal to u plus v, from where x is equal to 1/2 u plus v. Nice. And if I subtract equations, again, subtracting equations would be bottom minus the top, easier. So 2y squared, right? 2y squared would be, x's are dead, would be v minus u. So y is the square root of 1/2 of v minus u. And there goes your Jacobian, right? It's a square root. Because the square root of u and v, Jacobian is no longer going to be just numbers. Now it's going to be functions. Because of chain rule. Good. Well, not good, but good. So we'll have to keep this part for Jacobian eventually. We're going to use that. But we first transform the region, then we transform the function, then we transform, right, the rest. So let's go transform R into S region. So if I have this situation, how do I transform now? Well, we find the intersecting points, right? And you find intersecting points by setting equations equal to each other. So you have 4 of those to solve. I know you have to stay positive in life. Okay? Just stay positive. So okay, so let's see. Hold on. So this is x equals 16 minus y squared. This one is x equals y squared minus 4. You can be clever about this. This one over here. Yeah. So this one is x equals y squared, and this one is 9 minus x y squared. Look at your transformations, guys. Compare this and whatever fits. Which one fits? This one, right? Because if I move y to the v, right? Those two compare? If you look at it. So v is equal to x plus y squared. So if you put y squared on this side, you have x plus y squared, right? So how much is v? 16. V equals 16, right? So that equation up there is equivalent to v equals 16. Great. So do I have another one that it's like that? Yep, one on the bottom. V equals 9. And then over here, if I move y to the other side, x becomes negative 4. And over here, x is 0 on the bottom. Great. Well, that was easy, luckily. So how does the region look like? U and V. So V is 16 and 9. Okay. 5, 10, 15, 20. So 16 and 9. And then negative 4 and 0. Yes, there it is. That will be S. So region S is the rectangle. Rectangle that has the vertices negative 4, 9, negative 4, 0. No, negative 4, sorry. Negative 4, 9, and 0, negative 9. 0, 9, And then this one is negative 4, 16. And 0, 16. Good. So it's a rectangle. Transform our y squared. Well, y squared is clearly what? You have it here, right? Yes, 1/2 v minus u. And now Jacobian. Partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Awesome. Go. Both x's are easy. They're both halves. And both the y's are incredibly annoying because they are square root of v minus u over 2. So the derivative of that would be 1/2 of v minus u over 2 to the negative 1/2 times the derivative of the inside, which is either 1/2 or negative 1/2. So for the first one would be, so let me write it this way. This is going to be 1 over 2 times the square root of v minus u over 2, which brings the root 2 on top. Root 2 on top over 2 square root of v minus u. And then it's either times 1 or times negative 1, depending which one we need. So first one is u is negative, so it's going to be negative root 2 over 2 square root of v minus u. And then it goes positive root 2 over 2 square root of v minus u. Great. So Jacobian is further equal to what? 1/2. Oh, I don't need that. I have it already. Equals to root 2 over 4 times square root of v minus u. Minus and minus is plus another root 2 over 4 square root of v minus u. For the grand total of root 2 over 2 square roots of v minus u. And if it's going to make you feel better, put everything under the same root. there will be 1/2 square root of 2 over v minus u. I'm not sure if this will help or not, but that's what I have. Time to put our integral over region S for our y squared, which was what? 1/2 v minus u. Yep. Times the Jacobian, which is 1/2 square root of 2v minus u. And now, ladies and gentlemen, I'll just put dA because I have no clue whether should I go du dv or dv du, which actually never matters when you are on a rectangular, right? For the limits, but it does matter in terms of functions. What can you integrate, right? Because just remember the situation if you had, let's say, just e to the, let's say, v squared. Imagine if you had this. You clearly can't integrate dv first. But if you integrate du first, then u would pop here, and then that u would turn into a v, and then, right? So the question is, which one I integrate first? So I'm going to rewrite this one more time to deal with all of these numbers there. So I have a quarter, and I'm also going to kick out root 2. So I kick out all of the numbers, which is root 2 over 4. So this is out, and that's out. So all of those are out. And the only thing that is left is v minus u times the 1, well, actually I can write it like this. V minus u divided by the square root of v minus u, dA. Now, a little bit more of algebra there. If I am to put this under the root, it will pick up the square. So if I write a big root like this, it will be v minus u squared divided by v minus u, and then they cancel. So now I have root 2 over 4, double integral s, and what I get is just a square root of v minus u, and this is awesome. Because easy to integrate, right? So that's a square root of 2 over 4. And you can do, if you want, dv du or du dv, doesn't matter, but let's do dv du. V is from 9 to 16. And this one is from -4 to 0 for du. Square root of 2 over 4. Integral -4 to 0 here. Integral in terms of v is what? No one cares? Okay. So v minus u to the 3/2 divided by 3/2, computed from 9 to 16 du. This cancels, so root 2 over 6, integral -4 to 0, and then I have 16 minus u to the 3/2 minus 9 minus u to the 3/2, and I still have du. So square root of 2 over 6. And now we integrate in terms of u. You can't do u sub again. We can do g sub if you want to. I don't know. 16 minus u, that's g. And then dg is equal to negative du. right? You can do that if you want to. So it's clearly g to the 5 halves, which is 16 minus u to the 5 halves divided by 5 halves, minus, again, g substitution for the other one, which is, again, the same deal. From -4 to 0. Root 2 over 6. I can factor actually 2/5 out. So 2 will cancel, that's a 3 to 15, right? And now I only have to worry about 16 minus u to the 5 halves minus 9 minus u to the 5 halves from -4 to 0. So plug in 0. That's easy. When you plug in 0, that's a 16, which gives me 4. So you have 4 to the 5 minus 3 to the 5 minus -4 will give me 20 and 13 equals some decimal. No one cares what it is right now. That's the answer. So that was the first example where you saw that you do not get Jacobian. I almost said Jamil, I don't know why. Jacobian that is constant, right? We had it as a function, which could further complicate things. Yes? I did substitution in my head, and then I still use the original variables, which are the limits as is. Yeah. If I wrote this as g to the 5, then I better transform limits into a g limits. So that would further do more substitutions. How many necessary substitutions? Well, how many you need. That's the answer. Such is life. Yes.
Can you just go over the boundaries real quick?
Okay. So for boundaries, we were clever about it instead of forcing it. What you can do for the boundaries is you can take this equation equal to that equation and come up with what this point is in terms of x and a y, and then stick those x and a y here and come up with these, which would give you those 4 points that we had for the rectangle. Okay. You can do that. Or you can realize that this equation and this equation are the same form, which means that this b was 16. If you are to make them look the same, because if you notice here, if you are to move y squared to the other side, you will have 16 minus y squared, which is v minus, right? So v must be 16. So there's that, or you can transform the points.
I just didn't see that before we went to that equation.
Well, yeah, so this equation here and this equation here have the same type as that equation, and the other two equations are this one. So that's where I got 0 and -4, and right? So you can see it plus 0, minus 4, 16, and 9. And they all fit. Well, I remember spending hours with this because it was so interesting to me to kind of chase them around. Because each problem can be done differently in terms of, do you use a system, can you use the clever trick, do you transform the points? Because, you know, figuring out the region only is interesting, and then figuring out the rest, which is the rest. And then we have 3 variables with 3, which further complicates things to find all of the. I don't even know if the textbook solved any of those examples, because yeah, they give you. It's at least interesting to write. If you know what you're writing and you're careful about it, you can really pull one of those, what do you know? Let me just write the transformation for the 3D. See how that sits with you. So the triple integral over the region R of f of x, y, z dv would be the Oh, come on. Oh, we had the issue with the network. It's not. Okay. All right, fine. I'll have to. Oh, come on. Exactly. Oatmeal, yeah.
This is gonna give me diabetes. Where's the coconut?
I ate them all.
Hey, Nick, why is the math book always upset?
Creativity problem.
Because